Hi, in this video we are summarizing and illustrating how to model the dynamic response of structures subjected to different kinds of excitations. The general methodology to compute the dynamic response of a structure consists first in, of course, having information about the structure, its geometry, the material properties, the boundary conditions, and the types of excitations that are applied to it. From that you can build a model, whether it is a mass spring model, a continuous model, or a finite element model. Using one of these models, you can extract the modal properties, which are the natural frequencies, and the mode shapes. And with that, you can project the equations of motion in the modal basis and perform a truncation, which means keep a certain number of modes. Once you have these equations, this reduced set of equations in the modal basis, you can compute it using the methods described for single DOF oscillators, because each of the mode shapes is considered as an S-DOF. Once you have solved the problem in modal coordinates, you can recombine the mode shapes and modal amplitudes to go to what is of interest for you, which is physical coordinates. Now, there are two types of computations. If you are interested in a frequency domain response, which corresponds to the response of your system when you are exciting with an harmonic force, then the solution is given by this modal expansion on n modes here, and you recognize the mode shape of the system, the natural frequencies, and the modal damping of each mode, as well as the modal masses. So all you need to do is to compute these mode shapes, compute the natural frequencies, have an estimate of the damping, and you can build this transfer function. If you are interested in time domain responses, this is the equation of the modal amplitude of one mode, the general equation, and in order to solve it, we have seen that it's possible to express the impulse response of that mode with its specific modal damping and modal natural frequency, and then to do a convolution with the input force in the time domain, which gives you the response for each modal amplitude in the time domain. Then you can recombine by summing the contribution of all the modes with the given modal amplitudes in the time domain. So in this case, it gives you the value of x, the vector x, which is the displacement of all the degrees of freedom in your system, as a function of time, whereas in the first case it gives you this displacement at all degrees of freedom as a function of the excitation frequency in the system. Whatever the type of model you choose, the first step always consists in computing modal properties. So here we are presenting the mode shapes and natural frequencies of a 30-story building, which is modeled with plate and beam finite elements. So you see that the first mode is a bending mode in this direction. The second mode at a slightly higher frequency is a bending mode in the orthogonal direction. The third mode is a torsional mode, and then you have the second bending mode in the same directions as the first one, and the second bending mode in the orthogonal direction. This is the example of the plate that we have seen in a previous video. So if you take a rectangular plate that is clamped on all edges, this is what the first mode will look like. This will be the second mode, the third mode. The fourth mode involves now vibration in waves in the orthogonal direction. This is a combination of the two directions. And here mode number 6. Another example is here a practical example of a footbridge in Durbuy in Belgium, which was designed by Bureau Grège, and these are the pictures of the footbridge that was built. So you see that the footbridge is made of two main materials. So the main span is made by steel and you have here some supporting concrete pillar. So this was modeled using finite element by Bureau-Grèche, and these are the first two mode shapes. So you see in the first mode shape you have a bending of the main span with a slight torsion due to the curvature of the bridge. In the second one you have a second bending mode of this main span. Note that mode 1 is around 2 Hz, so it's quite likely that there will be problems of vibrations because the pedestrians walking on that bridge have an excitation frequency of around 2 Hz. These are higher frequency modes, just for illustration. A last example is this 5-story building where each floor is represented by a single degree of freedom model with an equivalent mass and stiffness, resulting in a 5 degree of freedom model in total with 5 times the same stiffness and the same mass. And so for the given values which are here above, you can compute the mode shapes and give some kind of representation. So you have the first mode at 4 Hz, second mode, third mode, fourth mode, and fifth mode. And you see that as you go higher and higher, there is the wavelength of the mode is shorter and shorter. Once the modal properties are computed, it's possible to compute the response of the structure, and this first set of examples is dedicated to the case where these forces, the dynamic forces, are applied directly on the structure. As a first example, we are consider this cantilever plate on which a force is applied perpendicular to it at this specific location, and the displacement at the same location is computed. So we are using finite elements to model this plate, and we have seen the mode shapes of the plate in the, just previously. So we are building the stiffness and the mass matrices, and from there we can extract mode shapes and natural frequency, and then express the transfer function as a sum over n mode. Here we are taking 25 modes in the frequency band of interest, which is 0 to 100 Hz, and we are summing the contributions of all these single degree of freedom oscillators without damping. So you see that there are quite a lot of modes between 0 and 100 Hz. Now, usually there is damping, so we have the choice between different damping models. So for proportional global models, which are most often used, in the modal equation, in the equation of motion of one mode, you have the coefficient xi, and so you have different choices for this coefficient xi. One way is if you use Rayleigh damping hypothesis, which states that the C matrix in the physical coordinate is alpha k plus beta m, then you will have xi I, which is equal to 1/2 alpha omega I plus beta over omega I. So you have two coefficients to set the shape of the evolution of the modal damping coefficients. If you use a simple loss factor, you can show that it corresponds to taking a modal damping of eta over 2, where eta is the loss factor, and it will lead to a constant modal damping, so constant in frequency. Or you could just choose some kind of empirical model where xi I is taken from previous experiments. For each mode you can have a different value. So here, for example, we compare a Rayleigh approach with an hysteretic, which means the loss factor approach. So in the Rayleigh we only take alpha is 1/10 to the minus 4 and beta is equal to 0, which leads to a linear evolution of xi I with the frequency, and so the modal damping increases with frequency. With the loss factor, you see that by taking it equal to 0.03, the xi I is 1.5%, and all modes will be damped the same way, which is reflected in the FRF here. You see that for the orange curve, which with eta is equal to 0.03, all modes have the same kind of damping, the same shape of the peak, whereas for Rayleigh you see that the peaks at low frequency are much more narrow because they are very low damping, and if you go higher in frequency they are more and more wide. In this example, the 5-story building is excited by a force at the top. And as we have seen, there are 5 mode shapes. So if you project the equations of motion on these mode shapes, you end up with 5 independent equations of motions, which correspond to the equation of motion of a single degree of freedom system, of 5 different single degree of freedom systems. So by assuming that x is a combination of modal amplitudes and mode shapes, you can also add some damping to each of the single degree of freedom system in the form of a modal damping coefficient. And this is the equation you have to solve for each mode. Once you solve this equation in the harmonic domain, so you assume that the force is harmonic and so is the response, then you recombine with this equation and you get x in the frequency domain, which is the sum over the n modes of these expressions. So as an example, this is the response at the top of the building when it's excited at the top of the building as well. We have taken a damping coefficient of 1% and 5 modes, which result in the 5 peaks that you see here in the response. Note that on the numerator you have a phi j transpose f phi j. So this first part tells you how much each mode, this is the fi, so it tells you how much each mode is excited, and in this example you see clearly that the first mode is excited more than the second one, third one, fourth one and fifth one, which explains this decreasing trend in the transfer function. We can also look at the impulse response of the building due to a force at the top. So for the impulse response, again, we consider the system as a combination of single degree of freedom systems, of damped single degree of freedom system. Therefore, we know that the impulse response of these is given by this following expression. And as each mode is affected differently by the pulse, we have to apply a scaling factor fi here in front. This is the result of the combination of the 5 impulse responses of this type at the level of at level 5. So for the relative displacement of for the total displacement, sorry, of level 5. Now, if we look at in a little more details, we see that these zi's. For the first mode, you see clearly here the gray curve, so this is really dominant in the impulse response. For higher modes, you see first of all that the value the amplitude of these impulse responses are lower. This is due to the fi factor that we discussed just before, but you also see that they decay faster. So why do they decay faster? It is because of the exponential here, which is minus psi I omega I t. But actually the damping is the same on the 5 modes. They have 1% on each. So the reason the higher modes decay faster is because their natural frequency is higher. So this is a general finding that the impulse responses will decay faster as the natural frequency of the mode is higher. And so when you sum up everything, you will see that actually only in the beginning do you have a noticeable difference between the total impulse response corresponding to all modes and the impulse response of mode 1. So after a certain time, the system will only oscillate on mode 1 and have a clear decay with the frequency and damping of mode 1. We can compute the response of the top of the building using also a random excitation. So for this case, it's the same as before. So we are assuming that we project the equations in the modal basis. We need to solve this equation, but now where fi of t is a random excitation of the type given here, multiplied by an amplification due to the mode shape. If we use the Duhamel's integral, we just need to again compute the impulse response. which we can do for all modes and then combine as we did before, or we can just solve independently in the time domain the amplitude of each mode by convoluting the impulse response of that specific mode with the force of that specific mode. Then we can expand again to have the displacement in the real physical coordinates. So this is the example. You start from a random white noise excitation. Note that the Fourier transform of a white noise is a constant function. So this function here is not exactly constant, but pretty much constant. And this is because it's a sample function and it's not an infinite time domain signal. So you see that pretty much all frequencies are excited in the same way by this white noise excitation. Now, when we do the convolution with impulse response and recombine, this is what we get for the displacement at the top of the building, so level 5. If psi on all modes is 1%, and if psi on all modes is 5%, you see clearly that the magnitude of the response is decreased. The second set of examples deals with the case where the excitation is done through the basis, such as in earthquakes. So for base excitation, we take the example of an earthquake. So we have a recorded ground motion here, which is applied to the building. We can do the Fourier transform of this ground motion to have an idea of how many modes of that structure are going to be impacted. And so in this case, you see that the amplitude of the earthquake is important until 10 Hertz and then decreases, but still there remains some component up to 40 Hertz. So we have the choice to model this structure. We could use this equivalent mass spring system with different number of levels, or we can do a more complex finite element model. In any case, we will take here the example of the 5-DOF system. It's always the same approach, so we are going to compute the mode shapes, and from that we will have 5, in this case, independent single degree of freedom system to solve for, where here the force Fi has been replaced by this gamma I times the acceleration of the base. So we do everything as if we had a force applied to the system, but this force is equal to minus gamma I x dot dot 0. Which means that the transfer function can be computed with the same formula by replacing Fj by this expression here. And in this case, you see clearly that the first mode is much excited by the earthquake, whereas the other ones are much less excited, much less than in the case of the force applied to the top. So this shows really the clearly decreasing trend of the transfer function in the case of base excitation. Note that here we are solving for relative displacement between the 5th floor and the ground. Now, if you go back to the equation, so we are solving for relative displacement here. We have the M, C, and K matrices. We project in the modal basis, and we end up with the equations of motion for single degree of freedom corresponding to each mode, where you see that here we are solving now again for relative amplitude, hence the R here, and we have a force which is given by gamma I x dot dot 0. Then we can solve for these equations by using the impulse response of the system and convoluting it with the acceleration of the basis to then recombine and find the relative displacement with this sum. This is an example where this ground acceleration is applied to the building for different values of stiffness. So the initial value for which you had a natural frequency of 4.05 Hertz for the system, this is the black curve, and you see that if you increase the stiffness of the building, you multiply it by 10, then of course the natural frequency is multiplied by square root of 10, it's higher, and in this case you see that the fact that the building is stiffer will lead to less motion at the top of the building. This next slide shows the effect of damping. So if we take the case when the first natural frequency is about 4 Hz and change the damping from 1% to 5%, you see also that there is a decrease in the response of the structure. Now we can look at a more complex model, a finite element model, where here we have only used a 10-story building with beam and plate elements, and we can do exactly the same, so extract the mode shapes and then convolute the impulse response for each natural frequency with the ground acceleration. For example, to recombine, and in this case we are using 20 modes with a modal damping of 1%, so between 0 and 15 Hz, and you see that in this case the first mode of the building is at 0.8 Hz, and this is the kind of response to the earthquake that you will get as the relative displacement at the top. You can even make it more visual by making a movie. So because you have a finite element model, you have the displacement at all locations. So in this case you see that the earthquake is going to hit the structure around 10 seconds. So before 10 seconds not much happens, but you will see soon that when we arrive at 10 seconds the motion of the building becomes important. So here it starts. Note that we have of course amplified the motion. The structure, if well designed, will not move that much because it would lead to severe damage, but this is just to amplify the motion and show what happens. You see that after passage of the earthquake, which is now, the building is oscillating freely with the free decay of the first mode. In summary, when a structure is excited by dynamic forces, you can either consider that this excitation is in the frequency domain, meaning that you are going to apply an harmonic force of different frequencies to your system, or that you are going to work in the time domain with a given time history of your excitation, whether it is a base acceleration or an applied force. Once you have that, you have your model, and so you apply this excitation to the model, which is made of matrices M, C, and K, but usually you extract from M and K the modal properties. By doing so, you can project in the modal basis, and then you can compute the response of each independent mode, either in the frequency domain or in the time domain, depending on the type of excitation that you have used. The question now is, once you have done that, are these vibration levels acceptable? Are they not too high in some cases, or are they not high enough if vibration is what you are looking for, as for example in an instrument or a loudspeaker? And if the question is, if the answer to this question is yes, then you have nothing to do. I think you're ready to build your structure. But if the answer is no, you have to wonder how to reach these acceptable levels by either doing a completely new design or by using remedial measures, meaning small corrections to your design to reach these acceptable vibration levels. In this video, we have exposed and illustrated the general methodology to predict the levels of vibrations in a structure subjected to given dynamic loads.